Hello, my name is Rudy Fyles with another in our series of Statics 101, a program that explores structural engineering in real-life objects. Today, let's talk about the basic principles of statics. As the name implies, statics means a structure will stay in place. It will be static. In order for this to happen, three things need to be true. First, the summation of forces vertical needs to equal zero. The object does not move up or down. The summation of forces horizontal needs to be zero. The object does not move left or right. And finally, the summation of moments about the center of the object need to be zero so that the object does not continually rotate in one direction or the other. Let's draw a free body diagram to explore this concept a bit further. Here is a lever arm emerging from a center point on the left side. We are going to apply a moment of 1 foot-pound on this node. The length of the lever arm, hypothetically for this problem, will be 1 foot. Even I can do this math. Thus, in order to achieve 1 foot-pound of moment, we will need to apply a force of 1 pound to the end of the lever arm to achieve the counteracting moment of 1 foot-pound in order to keep the free body diagram static, thus not rotating in space. Let's explore this concept a bit further. Here what we've done is reduce the lever arm to 1/2 foot, and as you can see, the force in a downward direction now has been increased to 2 pounds. So 2 times 0.5 equals 1 foot-pound, i.e. again, the moment to counteract a 1 foot-pound moment applied in the opposite direction. The object remains. Again, we've reduced the lever arm to 1/4 foot, and as you can see, we now have to apply 4 pounds of force in a downward direction. 0.25 times 4 is equal to 1 foot-pound of moment in the opposite direction of the one applied at the center, thus the object is static. Let's take a look at a real-world example of this. After all, that's what we're all about. Here we have a roll of toilet paper. For illustrative purposes, I've superimposed the free body diagram onto the roll of toilet paper. As you can see, we have the 1 foot long lever arm, and we have the moment in the center of 1 foot-pound in the negative direction. This could be considered the friction of the wheel as you pull it in a downward direction on the paper. So, as we've already learned, in order for this to work with a full roll of toilet paper, we apply 1 foot-pound of force, just a little bit more, then we get paper. Now, naturally, this 1 pound of force has to be absorbed in the fabric of the paper itself in shear. As we've all experienced, typically full rolls of toilet paper are not problematic. However, as we also know, the amount of paper diminishes. Let's look at a roll which is now diminished to 6 inches or 1/2 foot. We now have to apply 2 pounds or more to keep it moving to obtain paper. Thus, the shear stresses on this paper are now 2 pounds. Again, as the roll diminishes and we are now 1/4 foot from the center, we are now having to apply 4 pounds of pressure to the same paper and starting to sweat bullets about getting enough paper, because as we all know, it starts tearing because it is reaching its maximum tensile strength. To make matters worse, as we approach the very center of the roll of toilet paper, our lever arm is diminishing to 0, and as the lever arm diminishes to 0, the amount of force in a downward direction that now has to be resisted and sheared by the paper approaches infinity. Thus, every roll of toilet paper will tear eventually. This is a life lesson we have all learned. So, the lesson for the day is, this is why paper tears as you approach empty. I hope you've enjoyed this lesson today. Until next time, this is Rudy Fyles with Statics 101.